Our topic today is the size of a set, the cardinality of a set in a precise way, comparing two sets for size. When are they the same size? When is one bigger than the other? This starts with an unofficial story of how counting was invented. Nobody can really say how truthful this story is because the origins of counting are older than history itself. But this story is plausible, and in any case, the point is it offers us a valuable insight into the nature of counting. Let's say back before numbers were invented, a herdsman has a number of animals. Every day he needs to check that they're all there. He has saved a stack of stones that are the same in number as the number of animals he keeps. So to check that the animals are all there, he holds the stones in his right hand, stands, watches the animals pass by him one at a time. As each animal passes by, he passes a stone from his one hand to his other hand. So if no animals are missing, he should find that the last animal passes by at the same moment when the last stone changes hands. If any stones are left over in his right hand, he knows he's missing an animal. So he's effectively making use of a one-to-one correspondence between the set of stones and the set of animals. Later, he realizes that a collection of actual physical stones is not necessary. He comes up with names for possible number of stones, and at the heart of this approach then is the use of a one-to-one correspondence between two sets to show that they have the same size. Having names for each possible set size, that is, each cardinality, is a convenient proxy for the set of stones. We can make this idea work for any sets, even for infinite sets, if we're just careful. Let A and B be sets. If there's a bijection from A to B, which is to say a one-to-one correspondence, that means one-to-one and onto function, then we say the two sets have the same size or the same cardinality, which is written in symbols like this: size of A equals size of B. If there is an injection from A to B, that's a one-to-one mapping, not necessarily onto, then we say that the size of A is at most the size of B. Note that this is the same as saying that A has the same size as some subset of B. We don't yet have names for the possible sizes of sets, which is to say the cardinal numbers. First, we define having same size, and then later you come up with names for the sizes themselves. So here is an instructive example. Take the set of positive integers, which I've called fancy n, blackboard bold n. Also, we have the set of non-negative integers, that's n sub 0. This set is the same as the natural numbers, union a single element 0. These two sets have the same cardinality because we have a bijection between the two sets. I've shown you one. It's just the function that subtracts 1 from everything. So please note that although we have added a new element to our original set of natural numbers, the resulting set, the new set, still has the same size as the original set, exactly the same size set. So this fact, and it's a fact, it has bothered a lot of people, even serious mathematicians, from being willing to talk about the size of sets beyond finite sets. And before we go any further, let me just remark about the notation. I've highlighted here two different kinds of arrows that we use. The first arrow is used when specifying just the domain and range of a function. It just says that the function maps elements of the first set n to the second set n sub 0. The second arrow is on the level of individual elements. It's the arrow that we call maps to. So this more specifically identifies the image of each individual element. It says f of x is x minus 1. Don't confuse the two arrows. Please use them consistently in mathematical writing. It's necessary in order to be unambiguous. If you don't clarify, then there can be ambiguity. Back to business. Now, it's easy to pick out an injection from the left side to the right side. You just map x to x. And that's one-to-one and not onto. But nowhere did we ever say that that makes the first set smaller than the second. What we said is it makes the first set in size less than or equal to the size of the second set. No problem here. And in fact, you could go the other way by pointing out that there's a function h, mapping x to x plus 2, that's also an injection from the set on the right to the set on the left. What does that say? Well, once again, it just says that the size of n0 is less than or equal to the size of n, which is true. I mean, if they're the same size, then of course you have less than or equal in both directions. Pushing this idea further, the set of natural numbers has the same size as the set of all integers. I've listed the natural numbers on the left, the integers on the right, and then there's an obvious bijection, which I show by the function f with these red arrows. This is a bijection. Again, no surprise, since both sets are infinite. Never mind that one is a subset of the other. Doesn't matter. This gives less than or equal to in one direction, but actually you get in both directions, so the two sets actually have the same size. I've not written down an explicit formula for the bijection, but you can clearly see what it is and believe that it is a bijection. And most of the time, we're just happy with that. If you ever did need an explicit formula for this function, here it is. But that's not the point. And by the way, when I've listed the elements of the set, I haven't listed them in any kind of numerical order. That's not the issue here. When you talk about comparing like a set of stones with a set of sheep, you're not going to list them in order. And what you mean what's order? What order? I mean, it doesn't matter what the order is. We don't really have an order a priori. We can stretch this idea even further by showing that the entire set of rational numbers has exactly the same size as the set of natural numbers when we get through the argument. So the rational numbers can first of all be laid out in this infinite table. Infinite array has infinitely many rows and infinitely many columns. In the first row, we list all the integers. That's the rationals with denominator 1. The second row has all the rationals with denominator 2 in lowest terms. The third row has all the rationals with denominator 3 in lowest terms, and so on. Every rational number pops up exactly once somewhere in this table. Now you can find a path that kind of snakes its way through the entire table, as shown starting in the upper left-hand corner and zigzagging around. This path passes through every entry of the table exactly once. And then to get the required bijection, you just go through this path and write down each number as you come to it. So for each natural number n, it corresponds to the rational number that is the nth position along this path. So the sequence of rationals you get is 0, 1, a half, a third, minus a half, minus 1, 2, and so on. And this is not any kind of numerical order, but it is a sequence that hits every rational exactly once. So the set of rational numbers has exactly the same cardinality as the set of natural numbers. So we emphasize that having the same size, according to our definition, is an equivalence relation, as it should be. If there's a bijection from A to B and a bijection from B to C, then simply compose those two bijections to get a bijection from A to C. This shows that having the same size is transitive. Obviously, the relation is reflexive. The identity map on a set, taking x to x, is always a bijection from a set to itself. Also, the relation is symmetric, because if you have a bijection from A to B, then the inverse function becomes a bijection from B to A. Now, a cardinal number I've used this term? Well, it's just a name for each equivalence class under this relation. And according to our apocryphal story, this would be the origin of counting sizes of sets. Now, in my first video, I asked what the number 2 means, or how it should be defined. So at least in the context of counting numbers, or natural numbers, let's say, if by 2 you mean the cardinal number 2, this could be defined simply as a name for the entire equivalence class of the set I've shown you. It doesn't matter what these 2 elements are, as long as it's 2 elements like this, and you write down one set with 2 elements. Pick any such set. I'll take bananas and strawberry for the 2 elements. Then it will have an equivalence class which defines the number 2. And if you had 2 other elements, then we would still be thinking of the same equivalence class. So it's a universal concept. In some of my examples, you might find it disturbing at first that a set can have the same size as a proper subset. This phenomenon never happens for finite sets. So if I have 18 stones corresponding to 18 sheep, and one sheep goes missing, there's no longer a one-to-one correspondence. But for an infinite set, however, if you take away one element from an infinite set, you're left with a set that has exactly the same size as what you started with. You might think that's weird or bothersome. Actually, I would say it is the definition of what infinite means. That's how the easiest way probably to define infinite. A set is infinite if it has a proper subset the same size as the original set. Otherwise, the set is finite. Now, we may view n sub 0 as the set of all finite cardinal numbers. These are just names for equivalence classes of finite sets. That is, all the sets that are finite according to our definition. So the finite counting numbers emerge from more basic notions from elementary set theory. This is where the first of the big 5 number systems comes from. It's from counting. Now, we say a set is countable if its elements can be put in a list. By a list, I mean either a finite list or an infinite list. I've shown you what they would look like in our notation. Each list can be indexed 1, 2, 3, and so on. If the list stops after n terms, then it's a finite set. Otherwise, it's infinite, but still only countably infinite. So it turns out that some infinite sets can be listed like this, and others cannot. That the list is too big to be listed. You can't put all the elements in a list, even an infinite sequence. And we'll get to that in the next video, but some countable sets are finite, some are infinite, and then we call them countably infinite to specify. By the way, I've seen a couple of authors of undergraduate analysis books write countable when they really mean countably infinite. So just watch out for different authors' choice of terminology. Note that a countable set is the same as a set having an injection into the natural numbers. This injection may or may not be bijective. In the bijective case, you have countably infinite. Here's your first infinite cardinal number. I'm giving you its name. It's the cardinality of any countably infinite set. Take your favorite one like the natural numbers. Then the cardinality is denoted aleph sub 0. The letter aleph being the first letter of the Hebrew alphabet. We use Greek letters so often in mathematics. Now it's refreshing to see Hebrew letters get used for once. By the way, this name is often spoken aloud as aleph naught or aleph null. So naught and null are names for 0. Probably more common on the other side of the Atlantic. So some basic facts, really, not hard at all to prove. If A and B are countable sets, then so is their Cartesian product, which means the set of all the ordered pairs from the 2 sets. The idea for proving this is essentially visible in our proof that the rationals are countable. So you just look at a table where rows are indexed by elements of A, columns indexed by elements of B, and all the entries in this table can be just the ordered pairs, and then you snake your way through this list And if A is countable and B is countable, you're eventually going to get through this whole list with a sequence. So for example, the set of all points in the xy plane with rational coordinates. That's going to be a countable set. And then Q3 is all ordered triples of rational numbers. So you can think of it as Q, Cartesian product with Q squared. So I'm putting together a Cartesian product of two countable sets, once again, countable. This is, if you like, the set of points in 3-space with rational coordinates. So is the n-tuples of rational numbers for every positive integer n. All of these are countable sets. If A and B are countable sets, then so is their union. So a union of two countable sets is countable. A finite union, in fact, of countable sets is countable. But more than that, countable unions of countable sets are countable. That is, if you have a sequence, A1, A2, A3, and so on, and each of these sets is countable, then their union is still countable. Now here is an example, and I'll make use of it later. What we call an algebraic number is a number that is a root of a polynomial with integer coefficients. So algebraic numbers can be complex, they can be real, but let's just say inside the complex numbers, you take the numbers that are roots of some polynomial with rational coefficients. The algebraic numbers is a very large set, includes much more than the rationals, but it's still only a countable set. Here is the proof. It's a union of countably many countable sets. An, I could write for the roots of the polynomials with rational coefficients of degree n. So a polynomial of degree n with rational coefficients is given by an n-tuple of rational numbers. And each one of those has only a finite number of roots. So you have only a countable number of polynomials of each degree with rational coefficients. So then you take the union of all those roots, and it's a union of countably many countable sets. So it's still countable. Moving on to some other examples. I haven't told you yet about the reals being uncountable, but for the moment, let me point out that the entire real line has the same cardinality as just the open interval 0, 1. And this one is more graphic and explicit than the previous examples. You just write down this function, and its graph, you can see it's an increasing function. So it's 1 to 1. And the limit on the left is 0, the limit on the right is 1, so it's on to the open interval 0, 1. So it's a bijection. And the graph tells you what that bijection is. So that's two sets with the same size. Once again, one a proper subset of the other. Nevertheless, they have the same size. Now, what about other kinds of intervals? Well, all the open intervals can be dealt with in the same way. In fact, every open interval AB has the same cardinality as every closed interval AB, or every half-open, half-closed interval is still the same size. But let's not move too quickly. If you just take the open interval 0, 1 and the open interval AB, these have the same cardinality because of a very simple-looking bijection, which is a linear function. And here's the formula, or the graph. So to come up with a bijection, in this case, a linear function will do the trick. But if you're trying to show that the open interval 0, 1 has the same cardinality as the closed interval 0, 1, this is true, but there's no continuous function that you can use as a bijection. Just isn't one. There's going to be infinitely many discontinuities. Now, I do want to convince you that these two sets have the same cardinality. And here's an argument why the open interval 0, 1, as I've said at top, should have the same cardinality as the closed interval 0, 1. First of all, closed interval 0, 1 is a subset of the open interval -1 to 2. So you've got less than or equal there for the sizes. And then I've explained why any two open intervals have the same cardinality. So this is also the same cardinality as the open interval 0, 1. And once again, the open interval 0, 1 is a subset of the closed interval 0, 1. And now you've got less than or equal throughout, so everything here should have the same size, right? But wait a minute. What is wrong with our reasoning? The way we defined having the same size and having size less than or equal is in terms of injections and bijections. So we didn't prove that trichotomy holds for sizes of sets. It does, by the way, but only if you use axiom of choice. Right now, let me just point out that you can get a bijection here without requiring the axiom of choice. And it's not easy. Show me a bijection between the closed interval 0, 1 and the open interval 0, 1. Well, it's elementary, but it takes some thought. All you have is injections going in both directions, and that's not the same as having a bijection. At this point, we have to either come up with a bijection, or we need a theorem that says if the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A, then they're the same size. And there is such a theorem. It is the Bernstein-Cantor-Schroeder theorem, or various combinations of those names. I think I've seen it referred to in about 8 or 10 different ways, depending on which subset of the 3 names you list and in what order. Now, this theorem has an amazing history, spanning several decades, many decades, close to a lifetime, during which famous mathematicians wrote to each other, asking if such a statement could be true, and supplying incorrect proofs and correct proofs in special cases, and so on, and arguing about the question, and doubting if the theorem ultimately were even true, and so forth, until finally we have a proof. And that might not be surprising if this were actually a difficult or deep theorem. But actually, it's a fairly straightforward argument. I'm not going to go through the proof, but I will tell you that it is elementary. I could do it in an undergraduate class easily in 10 minutes. But the problem was that this was new territory to everyone at the time. They had no prior experience with comparing sizes of infinite sets, so it just didn't occur to them how to get the job done. And the thing is, the functions that we're using here, they're not the kind of analytic formulas that people were used to thinking about. They just are functions in a more basic way, and it's hard to write down really explicit formulas. So when I show you the bijection between our 2 unit intervals, you'll see why they would have a hard time thinking about it. But I will also tell you, this theorem is not only elementary, it also does not require the axiom of choice. This much does not require the axiom of choice. So it's a fairly explicit way to come up with the bijection between A and B. Now, let me show you a bijection between the closed interval 0, 1 and the interval including 0 but not 1. So that's not all the way to answering the previous problem. I'm going to show you a bijection, first of all, in this case, and then we'll get the whole story afterwards. So here's my function. I define f of x to equal just x most of the time, that is, unless x happens to be a fraction of the form 1 over n, in which case you map 1 over n to 1 over n plus 1. So the graph has infinitely many discontinuities, all of which occur at the points 1/2, 1/3, 1/4, 1/5, and so on. We just push each of these points along to the next one, and everywhere else you just take y equals x. Once you have the idea, it's not hard to also find a bijection from the closed interval 0, 1 to the open interval 0, 1. There's more than one way to do that, but here I'm putting together such a bijection G by using 2 instances of the f listed above. And essentially, the first application of f takes care of the left endpoint, and the second application of f takes care of the right endpoint. You can think about this. Of course, the description is rather complicated, and the actual graph is highly discontinuous, but this is unavoidable if you're looking for bijection. You can't come up with an explicit bijection without having infinitely many discontinuities. Now, the proof of the Bernstein-Cantor-Schroeder theorem in the general case has to do something like this in general. So you have these infinite cycles, like the one that I've listed here, and you sort of push people along the chain. To be honest, the proof in the general case is probably easier than this special case.